future. Okay, no other questions? Let's thank our speaker. Next speaker is Professor Marlan Scully from Texas A&M University. Marlan Scully was John Dowling's mentor when John was at the Max Planck Institute.
Before John Dowling was John Dowling. I was his mentor before John Dowling was John Dowling.
Before John Dowling was John Dowling, he was the mentor of John Dowling. Yes, then the influence of Marlan Scully on John Dowling seems to be permanent. Yeah, many occasions I saw John is in some kind of times of decision, and he talked to me, what would Marlan Scully do? So that question seems to me that the guiding light for John, perhaps. And the quotation, John has weekly Zoom meeting on every Wednesday afternoon, and Marlan Scully is the most frequently quoted one, perhaps after Albert Einstein. But most of the former student and current student, yeah, probably know this quote. The quote goes like, if this problem is too hard for everyone else, it is just right for us. Did you ever say that?
That's good.
So that was the mantra that John wants his students to inherit. So, yeah, ladies and gentlemen, here is a National Academy of Science member, Professor Marlan Scully.
Thank you. Great kid. We all knew he had great talent. Jonathan Dowling was a wonderful student of Asim Baru, a wonderful professor, University of Colorado. Jonathan's first postdoc was with us in Germany, right, at the Max Planck Institute. He was in my group. Oh, by the way, the order of speakers is correlated to the number of years that you had the pleasure of knowing John. 1, 2.
I started earlier.
One of the aspects of John's career that you might not be aware of is that he was interested in relativity and Unruh radiation. How many of you here are friends with Unruh radiation? And how many of you have never heard of it? Fair enough. Unruh radiation is one of those topics that, as I hope to convince you, you should learn about just because it's fun and because there's a lot of payoff. But in particular, by starting with special relativity and giving yourself the edge of knowing about Unruh radiation, it's an easy step to general relativity, black hole horizons, and so forth. And so in particular, I'd like to try to concentrate today to the point that I can have you read this embarrassing abstract. I say it's embarrassing because I didn't mean to send this abstract with this talk. That's okay, because you won't read the abstract and hopefully you won't be too much distracted by this talk. But by the end of the talk, you'll be able to read the paper that appears in Physical Review with Bill Unruh and others. So beginning with our activity in this direction, and by the way, Mr. Chairman, I never exceed my time. When did I start? When the big hand was on the 7, right?
You're fine.
Okay. give me a 10-minute warning. So I'm at Texas Atomic and Molecular University. And in particular, I enjoy small universities. Is there a pointer here that somebody knows how to use? No, I don't need that. I've got the, presumably I've got this.
Just the top.
Yeah, but I'd like to have a pointer,
This is a screen button, right?
the screen. Good. So this is Texas Atomic and Molecular. This is oil. Small universities are my passion. I love small universities, like Princeton. It's the biggest small university in the country. Baylor in Texas is one of my favorite schools. As a diehard Baptist, I appreciate these kinds of schools. Princeton is a Presbyterian school, by the way, and I invite you all to come and visit us there and see what we're doing in areas of interest. But in particular, I'd like to focus on the interface between John and these kinds of problems, Unruh, Hawking radiation, and entanglement. So here's a picture of John in the period when he was a postdoc with me for the second time, and thus second quantization. First time in Munich. Had a great interaction with him. He's a great kid. And then he left and went to work at the Missile Command in Huntsville, Alabama, with Chuck Bowden. It was a great place. They did a lot of really good physics there in the old days. And then they ran out of money. And so John came to me in Texas, and we were sitting around lunch, and he said, well, what should we do together? I had just come back from a conference in which we were talking about the advantage of quantum instrumentation, atom gyros, okay? With an ordinary laser gyro, you can measure the rate of rotation based on the number of wavelengths fitting around a given circuit. With an atom gyro, same thing, lots of wavelengths, however, because the wavelength of a Bose condensate is much shorter by the ratio of the energy of a photon, 1 eV, to the rest mass of the atom. So that's really a big deal payoff. But what about noise? Signal to noise. So we were at a conference in Brussels, a Solvay conference, and Jeff Kimball said, you guys, you theorists, really must tell us what's the signal to noise. Not just how much the signal is improved, factor of 1,000,000, but how much can we gain signal to noise? So I worked it out while we were still there and gave him a number and wrote up a few notes. And Jonathan saw these notes and he said, let's write a paper. So I said, okay, you write it. He wrote it and submitted it. I don't think I ever saw it, but we used second quantization, as you can tell. Jonathan made great contributions in quantum informatics, and he told me, and maybe one of you will explain it to me, that his work here stimulated his high noon states, his high noon interferometry work. Jonathan, as I said earlier, did his PhD thesis on general relativity and what he calls the quantum electrodynamics vacuum fluctuations associated with an accelerating observer. But the interesting point is that this paper and the work he did with wonderful Asim Baruch used classical radiation. It's not quantized radiation. In this context, what does he mean by first quantized? Well, waves, okay, Maxwell's equations. Second quantization is quantizing the amplitude of the electric field. And so in what he and Asim were doing, they were explaining acceleration, aka Unruh radiation, by looking at the problem of an atom interacting with some sort of stochastic field associated with vacuum fluctuations. And there used to be a lot of argument about whether the UNRU radiation was real radiation. And I don't know which side of that argument this particular paper comes down on. But for sure, John and his friends and colleagues, like Paul Alsing, where's Paul? Yeah, so when you're all done, you can go to Paul. When I'm all done, you can go to Paul and say, what the hell is he talking about? One of the things that I'd like to do in the next few minutes is explain to you what is UNRU radiation. UNRU, by the way, is now at Texas A&M. So we're very proud to have him. He's got a joint appointment between A&M and the University of British Columbia. Permanent. David Lee. You know David Lee, Nobel Prize in helium-3, etc. Came to me one day, he's at Texas A&M, came to me one day, everybody's at Texas A&M. He says, so how come black hole radiation goes like the area, surface area of the black hole? And I said, well, I'm not sure I can give you an intuitive explanation of that interesting question. Let me go away, work on it, I'll come back to you this afternoon. So I got my copy of Misner, Wheeler and Thorne, looked through it, wasn't there. So I thought, well, okay, how will we explain this to a super intelligent guy like David? UNRU radiation, right? Let's take an atom, drop it, it's accelerated as it goes into the black hole. We'll calculate the entropy of the emitted radiation, and maybe that's something related to Hawking radiation. Maybe the entropy is the same. Turns out to be dead on. But I'll tell you more about that in a minute. And in particular, go in the direction of explaining acceleration, UNRU radiation. The point is that if an atom beginning in the ground state accelerates through some region of space-time, having whatever, mirrors, some gravitational curvature, whatever, the atom will emerge on the other side with a thermal distribution. The probability of being in the excited state, A, is going like the Boltzmann factor, where omega is the frequency of the atom, and A, actually, that should be A over C. There it is, alpha. A over C is the acceleration frequency. Now, this interesting observation has a history. Who was the first to point it out? Well, UNRU. No. It's a guy named Jerry Moore. Now, Paul and I both know Jerry Moore because Jerry Moore is a distinguished Air Force scientist. He was a guy that I had the privilege of working with for 20 years. He was my assistant, started out as a postdoc, ran the group, did great quantum optics for 20 years. Oh, by the way, he did his thesis at Brandeis University, 1969, 1970, on the question of what happens when a mirror is accelerated. No atoms, just a mirror. He did the calculations, showed that the mirror would be surrounded by thermal radiation in some sense. Very interesting observation. Came to me as his first postdoc, gave us a seminar on the subject. We listened. Okay, but this is a very tiny amount of radiation. Didn't really seem that surprising. And so Jerry went off to work on things like free electron lasers and high power laser systems. Did a wonderful job throughout his career, retired now. But the Moore effect, the effect in his thesis, is now famous and has been seen by experimentalists, thousands of references to his paper. Never referenced for the first 20 years of its existence, But the guy here, Steve Fulling, saw the thesis and wrote his Princeton thesis on this question of quantum field theory and curved space-time. He didn't, by the way, he's a professor of mathematics at Texas A&M. Jerry Moore, he didn't refer to Jerry Moore, but Bryce DeWitt, University of Texas at Austin, that's a small school up the road. Bryce DeWitt does refer to Jerry Moore and gives Jerry a lot of points. Stephen Hawking saw Fulling's papers and used some of the mathematics and some of the ideas that Fulling put forth and came up with his famous 1975 evaporation of black holes paper. One of the really most amazing papers of the 20th century. Other people like Paul Davies and then Ivanovich. Who am I missing, Paul? Somebody else should be there. But anyway, Bill Unruh, shortly after Hawking published his paper, Bill Unruh, who was a student of John Wheeler's at Princeton, decided that he could really understand Hawking radiation by better understanding this business of acceleration of a mirror. In his paper, he didn't talk about atoms. He talked about the Jerry Moore problem, acceleration of a mirror. But he didn't know about Jerry Moore. He only knew about Fulling. So that's the background. That explains what Unruh radiation is and gives you some historical perspective on how it all came about. Peter Maloney, in his excellent book on quantum electrodynamics, talks about Unruh radiation and has a section explaining it intuitively, kind of. Doesn't really quite do it, but gives an interesting kind of motivation. And he notes there that a uniformly accelerated detector, neutral atom, produces this kind of radiation with that kind of temperature, where KB is a Boltzmann constant, everything else is obvious. But he then goes on to say, it's hardly clear why this should be the case. It didn't get discovered until half a century later. It was 1975 when our friend Unruh wrote his famous celebrated paper. 1925 when Schrödinger first came on with quantum mechanics. And by the way, in some of his early papers, 20, 25, 26, introduced the phrase quantum electrodynamics. Now, not only was Maloney interested in this business, but Feynman, at the time of his death in 1988, had on his blackboard subjects that he would like to better understand. Acceleration radiation is one of them. And this business of making acceleration radiation part of your toolkit, part of the sort of thing that you can explain in the elevator to your dean. By the way, you graduate students, always have your elevator speech ready. When you're a student, you want to tell your thesis advisor what you've been doing the last couple of weeks. When you're a faculty member, you got to tell the dean why you need this new faculty position. So let's make sure that we all walk away with an elevator speech on Unruh radiation, and in particular the Dowling interest in that. So because of interest in quantum thermodynamics, I started thinking about thermal radiation in different ways, and worked out a simple quantum optical explanation for this business of Unruh acceleration radiation. And it's very simple from the point of view of understanding ordinary radiation. A photon in ordinary radiation, okay, falls from the excited state to the ground state. By the way, the excited state is A, the ground state is B. Why isn't the ground state A? because we're laser physicists. And we start with everything in the excited state. No joke, Willis line. A to B, and a photon is emitted, or B to A and a photon is absorbed. High school physics. But now, let's consider the part of the Hamiltonian associated with counter-rotating processes. Excite the atom and emit a photon. That's allowed by quantum mechanics, but this is a virtual transition. The photon is reabsorbed very quickly. But what if I accelerate at the same time I'm emitting, so that before the reabsorption can take place, I scoot the atom out of the road, or at least partially out of the road. Then that indeed is the basis for acceleration radiation. Look at the Hamiltonian. We start with a creation operator. I got a nice pollen allergy. I don't have COVID, I guarantee you, but I cough a lot. Oh, I'm sorry. So, bottom line, the counter-rotating terms associated with creation of a photon and excitation of the atom is what we're talking about. But the proper time in the frame riding along with the atom with lowering operator signal tau is what's important. And we must rewrite the time of the photon in terms of the proper time. So the photon clock, in terms of proper time, will have the famous hyperbolic secant relations between time and space. So it's an easy matter to do the calculation. And from the quantum mechanical perspective, we're just doing first order perturbation calculation. Vacuum, atom in the ground state. Excite the atom, that is, go to the A state, emit a photon, one photon of wave vector k. Plug in the Hamiltonian from the previous view graph and do the integration over tau, because I'm asking, what's the likelihood that the atom will be excited? You do that calculation, takes you a couple of hours. It's a fairly complicated calculation involving the exponentials of exponentials, but never mind. When you're all done, it boils down to gamma functions. And what you find is that when you do this arithmetic, you get the famous Max Planck factor, the famous Bohr-Einstein. Well, come on, the famous Einstein result, in which Max Planck and Bose and Einstein all agree that we have this energy, because I'm going to put an H bar here and down here. So here's H bar times omega, and then the C over A is the acceleration frequency. Bam, you end up with exactly the Unruh radiation. Now that's interesting because you think that, well, the Unruh effect there is so simple that people must have this in mind when they talk about the acceleration radiation. Not so. There's much more to it, and the much more is page 25 in the book, which is the entanglement business. And I'll come to that in a moment. But first of all, then, let's go back to Maloney's statement, hardly obvious what's going on, and say it is obvious what's going on within the context of parametric down conversion. We take a pump photon, blue photon, and we get out green and red, right? And in particular, then, we look at the process of acceleration radiation, and we're extracting energy from the center of mass of the atom. That's like the pump photon, and we're exciting the atom and exciting a mode of the radiation field. So acceleration radiation is no more complicated and no less complicated than parametric oscillation. Remember, one of the neat things that comes from parametric oscillation is entanglement between these two photons. We're going to show in this paper with Bill Unruh, appearing right now in Phys Rev, that entanglement comes out from the point of view of this picture very neatly. Now, there's more to be said for all that, but let me go back to the David Lee question and talk to you for just a minute. How's my time? How are you doing? Well,
Fine, 10 minutes.
time's up?
10 minutes left.
Okay. So these are the guys that I was working on with the problem. Steve Fullen, Don Page was a Hawking live-in postdoc. And he lived with Hawking for many years, and he's now at the University of Alberta in Canada. Wolfgang Schleich is a big name in quantum computing in Germany, right? He's the guy who got €1 billion from the German government to start quantum computing at several universities. And Anatoly Shvydzinski is a research professor, colleague of mine that I'm very proud of. Okay, so what we do is we do this problem. We let an atom fall into a black hole and argue that it radiates. So I did the problem in sort of back of an envelope, maybe back of 2 envelopes. Nevertheless, I did a simple calculation and I got this answer. What do you see? Can you read it? Here's the frequency nu of the photon. And here's something involving Rg, which is the Schwarzschild radius, gravitational radius. And such an expression is exactly like what we had before, with acceleration now coming from the Schwarzschild radius. And now you can go through all this and calculate the entropy and find that you get exactly the same number, exactly the same expression that Hawking and Bernstein got. Bernstein and Hawking got. Bernstein first. So that's interesting. There are probably half a dozen nice intuitive explanations for this black hole temperature. But when you read them, you find that they typically don't get the factors the same. They don't get the 1/8 pi, the dimensions are always right, but this calculation gets everything the same. We call this horizon brightened acceleration radiation, H-bar radiation. And it's turned out over the last 4 years to be an interesting problem that several papers have been written on. Now, just to conclude, I mentioned that you can use this particular result to give you insight into the equivalence principle. And in particular, here's the point. If I accelerate an atom and I look at the Bose-Einstein factor, the Planck factor, it involves omega, the frequency of the atom. If I let the atom be stationary and I accelerate the mirror, that is to say, do the Jerry-Moore problem, then I get the frequency of the photon coming into the Bose-Einstein factor. That's interesting. And it's also intuitively understandable because now it's the radiation field that's affected, not the atom. So the frequency of the photons are what comes into the game. Now I come back to black holes. By the way, when I showed this calculation to Don Page, he said, well, no, it can't be true because an atom in free fall doesn't radiate. And you'll notice he's one of our co-authors. So we did convince him, and we convinced ourselves that what's going on is exactly the analog to the Unruh problem, but with the mirror accelerating, not with the atom accelerating. Okay, so here the atom is stationary, the mirror accelerates. Here the atom's in free fall, like stationary indeed, but there's a black hole horizon. Now, that's the end of my time and in some sense, the end of my story. If you look on page 25, you'll see pictures. And in particular, look at the pictures, please, associated with the, as I look at it, the right-hand side, okay? Oh, that's the black hole. Look at the left-hand side. That's Unruh radiation. What's Unruh radiation? The atom hops to the excited state, a photon is emitted. But now the atom's in the excited state, and it falls down and emits another photon. But these two photons are very different. The first photon has negative frequency. The second photon has positive frequency. What's he talking about? Negative frequency photons? Google it. You'll find articles saying there is no such thing as negative frequency. But there is, because I got a paper published on that page. Thank you for your. And thank you, John, for giving us the excuse for another part.
Yeah, I'm a little bit confused for part C here. When your atom is falling, it's according to free fall, where's the acceleration is in the equation of motion, but I thought it had to do with the experience of a force on the atom. When you accelerate the atom feels.
Okay, good. Can I recast your question
Yes.
this way?
Yeah.
So here, Scully, I understood what you said about the atom being gone before it could reabsorb the photon, fair enough. But here, it's not the same. It's the fact that the photon is indeed falling, but therefore in some sense stationary. So it emits the photon rides along with it. And so there's plenty of time to reabsorb that same emitted photon. That's what you might think. And that's the way Page and people of our persuasion, like Sam Bernstein, argue, okay? What I have to confess here is that there's a mirror in my mind's eye that you're not seeing. It's right here. And that mirror separates space here, which we call the Bolivar vacuum, and space here, which is the black hole, okay? In particular, then, the photons that are associated with this atom doing its dance up and trying to come back down are not free photons. Those are photons influenced by the horizon. Nothing much happens until you get very near the horizon. And then a photon that is normally a vacuum fluctuation photon has crazy features. And those crazy features, which are associated with the Lindner metric, are what this is all about. But that's exactly the right question.
So my understanding of the black hole radiation was that the wavelength of the radiation is on the same scale factor as the size of the black hole. Is that true? Do I get that picture from this part C?
I have a confession.
Yeah.
I can't see out of this here, I can't pee out of that one. So mostly I read people's lips, but I didn't catch your question. Can you repeat it for me?
So my understanding of the black hole radiation is that the wavelength of the radiation is set by a scale factor to do with the size of the black hole.
Yeah.
What length?
Basically, I thought it was around the wavelength of the black hole.
All right.
And so it's not blue compared to the size of the black hole. It's red radiation. Is that true in this picture here?
Well, the acceleration associated with the black hole radiation is governed by the radius of the black hole,
Right.
defined by the gravitational radius, okay? And so in that sense, it is true, okay? Paul?
So I'll ask a question to maybe I can help with this. So Marlon and I talked a little bit
Louder?
about this. Marlon and I talked about this last night, but I have a question. So I think the nice thing that he showed in the other picture is that when the, so you're right that the radiation is on the order of the wavelength of the short sail radius. But in the accelerating mirror, the radiation has to bunch up.
Yeah.
What happens is it bunches up, and that bunching up is like a choking effect. That's what parametric oscillation. So I asked Martin last night at this point about where's the mirror? And basically, if I understand what you're saying, is that the mirror is basically the Schwarzschild horizon. So here's my question, okay, sort of talking about last night, is that the Hawking calculation, and all these calculations don't have any back action. But you can think about if you have a mirror at the horizon, right? If the black hole shrinks by emitting Hawking radiation, that's like an accelerating mirror because it shrinks a little bit. And it's exactly like having a mirror that's accelerating, but you never really put in the back action in this, but it's there. But so the thing is, like, my interpretation of the mirror is, well, we know it's there, so we treat it like a mirror. Like, why a mirror at the Schwarzschild radius? So what I'm asking you is, have you thought about going beyond this to back action? That's the thing that everyone is struggling with. Is how do you put the back action? The black hole really is shrinking when it emits a little bit of radiation, Hawking radiation. Schwarzschild radius goes RG minus delta RG. So that's, to me, it's like you're accelerating. Mirror is that the Schwarzschild radius is shrinking.
In some sense, what you're talking about would be important on the Planck line. Important when you get down to.
Well, because the black hole will eventually get smaller and smaller and smaller, and
So
so it
let me-
will accelerate. And so that accelerating mirror is like the case that you have over your beam. that you have.
So let me answer your question from the point of view of the elephant in the room. Well, it's really not accelerating, so how are you getting the right answer? And again, I come back to the fact that what we did in this part of the column is to do the calculation for the trajectory of an atom falling into the black hole using Wheeler's tortoise coordinates. So we really are doing general relativity at this point. So this is special relativity, this is general relativity. We don't have any mirror, but we do assume a Bohr vacuum, which is achieved by putting a mirror separating the place.
So I can think of the mirror as a boundary condition, basically.
Yes.
You can think of it as kind of a bound.
So as you put that in to get the Bohr.
Yeah, I need the Bohr vacuum. That's exactly right.
Any more questions? So we will have a short coffee break. So that's all.